So Nancy's point is, all right, well, what about that issue you mentioned where we've loaded up a register in the CPU that the program is depending on? What if the OS code modifies that register, right? When we go back to the program, will things work? And the answer is, unless we have a solution for that, we have a problem. There is a solution for that, and the solution for that is using a data structure, which you learn about in your data structures class, but it's actually implemented in hardware with the CPU. The CPU has this data structure. It's called a stack. A stack, all right? So in the old days, we would go to a cafeteria, and in the cafeteria line, there'd be a tray, and there'd be a real plate. We used to have real plates back in the old days, right? And when you went to grab a plate, it would be in the spring-loaded mechanism where the dishwasher would bring the tray of plates that he had washed, and he would push the plate into the spring-loaded mechanism. He'd push a plate, then he'd push another plate, then he'd push another plate, so that there's a stack of plates waiting for customers. A customer comes along, grabs the last plate that was pushed, key point, and pops the plate off of the stack to put onto the tray. All right? So we push items onto the stack. The last item pushed is the first one popped. This is the way a stack works. So what happens is in the transition, we take all of the registers in the CPU. We take all of the registers of the CPU, and we is stack memory. And we push them onto the stack. Then we go to the ISR. So the state of the machine, the value of all of the registers, is stored away. And we call this can be called a stack, part of the stack, what's called a stack frame. The memory in the stack will contain all of the registers at a point in time when the interrupt occurred. We push them all. We push everything here. It's temporary, right? We go off and we do what we need to do. When we come back and we want to go back to this program, in fact, this address, this next address, we would call this the return address, right? That also typically gets pushed onto the stack. And this is also, if you've ever wondered in your programs, this is not hardware now, but in your programs, printf, right, gets called everywhere. When you get to the end of the printf routine, how does it know where to go? Ever think about that? You get to the end of the printf routine, how does it know where to go? Before you call printf, you push the address of the next instruction on the stack. You go into printf, you print the information. At the end of printf, you jump back to that address that got pushed onto the stack. Right? So GP1 gets loaded in program 1, right? We have an interrupt, so we push GP1 onto the stack. We push the address that we're going to be coming back to in program 1. We go off and we go into the OS code. The OS code literally uses the registers Doesn't worry about using them because they're saved away now. Okay, and when we are done here, what happens is all of these registers get returned from the stack. They get popped. They get popped. It's a very terrible drawing. I apologize. Right, it's a terrible drawing. I'll get some better drawings for you. But we pop the information, and so Sean, this is the cost, right? This context switch of going from one program to another involves push, 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 and then eventually pop, 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 pop. And all of this is instructions that take time. All right. Questions? Yes, John. Could you be more specific what you mean by regular? The question is there a way to regulate the number of programs? Yeah, to the best of my knowledge, John, to the best of my knowledge, there isn't a configurable in the OS that so that we could tell Windows, let's say, don't start more than 100 programs or something like that. But what we can do is we can observe what programs are running, and we can ask ourselves, do we need them to be running? All right, so when you're talking about performance tuning of the machine, there's a website that I'm going to be sharing with you. I don't have it off the top of my head right now, but there's a website. I think if you Google for this, System Internals Windows, if you have internet, you could Google for that. System Internals Windows. It'll bring you, and it should be a Microsoft website. It should be within Microsoft. There is a collection of programs that are very useful for understanding how the computer works, and also for performance tuning. And one of those programs is called auto runs. So if you run this program auto run, what it does is it goes and it looks at the registry in your computer to figure out what programs will start when your computer turns on. And you can then, with this program, you can select which ones you don't want to start. It will go make the updates into the registry. Right, so you may have many programs starting that you really don't need. Okay, you need to take care when you're disabling that you don't disable something that you do need. Absolutely, this is the point I'm making. Yeah, so you don't want to make that decision in a vacuum, right? You want to understand whether or not So you would have to research, and the information's available. So I mean, there's plenty of people who have had the same concerns or desires to tune the performance. So you would investigate the purpose of the process, what dependencies there are with other processes. This is research that you have to do, work that you have to do. And then if you find that, oh, I understand it and I don't need it, then you have it not start up. And that's how you'd approach that, John. There isn't some number that you say, oh, 100 and that's it. Okay? All right. Yes, sir. Yeah. Well, can I, before you ask that question, let me bring up a point. And in fact, architecturally, this is a question, a concern, right? A stack, the implementation of a stack can be one of two ways, right? I could have a stack that grows down, or you could have a stack that grows up. Right? And that at one point in time was dependent on the processor that you're using. I think I would, if I were, I can't say for certain, but I think if you investigate it, I think that that's a configurable now. I think that we can tell the processor which way we want it to work. But in the old days, depending on the processor you were working on, one would grow down, one would grow up. Right. All right. So now ask your question. Not to my knowledge, there's no advantage. If there is, it would be at an extremely. Yeah, no, I think there are some things that it's just what they decided on, and this is a related kind of topic is this idea of endianness, which I'm not sure if we've talked about that yet, but I have a presentation on that, where when we're numbering the bytes within a word, right? There's two approaches to how you do that, right? And so it's I think some of these things are one company decided to do it one way, another company decided to do it another way, right? Right. Right. So there we can have issues with the stack. We can have what's known as a stack overflow, So memory, if we've set up a limit to the amount of memory that we have in stack, we have some limit here, and we try to push more information onto the stack when it is full. This is called stack overflow. Okay, and it's something that can occur. So for you programming type people, are you familiar with the topic of recursion? Recursion. Excellent. A function calling itself, right? A function calling itself. So what happens is when one function calls another function, it pushes the return address on the stack. All right. So some algorithms use this technique called recursion. It's kind of a way of creating a loop, right? So if we were doing, I'm making this up as we go, search left, okay? And then somewhere within this function, there is a call to search left. What's going to happen is when we reach this point here, we're going to push a value onto the stack, and then we're going to come back into the function again, right? And then we're going to reach this line of code again. We're going to push another value on the stack, and then we're going to come back into the function again, right? And the algorithms, this is good. Algorithms often can be solved and well understood this way because we're for example, for you Linux people, when we type ls-R, it's the recursive listing of the directories, right? So we go into a directory, then go into the subdirectory, go into the subdirectory, go into the subdirectory. So it's a natural description of what's going on. The problem is the use of the stack by having so many function calls when the code is running, that sometimes when we have recursive algorithms, we can run out of stack because of all those function calls and all those pushes of information onto the stack, right? And something to be thinking about. All right. So what's the solution there? If we have control over the size of the stack and we want to increase it, we could. Or I've seen situations where we had to rewrite the code and not use recursion because recursion caused the problem. The use of recursion caused the problem. All right. So this technique of having the code call itself, this is recursion. Right. Recursion. Yeah. This is a programming topic, actually, but it's helpful to discuss in this assignment. Well, we want it to end, right? So somewhere in the algorithm, is a decision statement that doesn't cause us to re-enter the code. Yeah, absolutely. I'm waving my hands about how that works, right? Obviously, it has to end. But here's the issue: if it's going to recurse enough times before it reaches the natural end, and that number of times causes us to overflow the stack, that's a problem. All right. All right. We good with this topic? Yeah. All right. So this is how we can have scheduling. This is called preemptive scheduling. Preemptive scheduling. We'll be talking about scheduling in and of itself at another time. But this now is, the operating system has ultimate control because it gets control of the machine every interval, whatever this interval is, and then it can make the decision of what program can run again. Here's the other use of interrupts. If we have an I/O device, let's say we have the NIC interface, right? The network interface, and that network interface is connecting out to an Ethernet here. And every once in a while, a frame comes in that's for our computer, right? Every once in a while, an Ethernet frame comes in. Right? How do we process that frame? Right? So we're going to see that there's two approaches to I/O. Right? I/O standing for input and output. Right? Two approaches. One is interrupt driven. The other is polled. So polled works like this. Within our program, maybe in the OS, in the ISR, we could go out and we could read a register in the NIC chip to see whether there is a frame present. There could be a register in that chip that we read to see whether or not a frame has come in. So at some interval, we would say, is there a frame yet? Is there a frame yet? Is there a frame yet? This is called polling, right? Polling. Is there a frame yet? Is there a frame yet? The problem with this is most times there isn't a frame yet. So all of those times that we go out to read the register is a waste. It's simple. The approach is simple. It's well understood. We're going to, at a certain point in our code, we'll go out and we'll check for a frame, and if there is one, we'll handle it. The code for that is simple, but it's inefficient. We can have the NIC chip interrupt the CPU. We can have the NIC chip interrupt the CPU. Like the timer chip interrupts the CPU. We can have the NIC chip interrupt the CPU so that we can be executing instructions without having to poll that chip over and over again. We can be happily running a program, and then when a frame comes in, the NIC chip will interrupt the CPU. Yes, John.
Not from the internal computer, but from the network. That's how that interrupt will work.
Well, in both of these cases, we're discussing hardware interrupts. One of the interrupts is timer based.
Right.
The other is a chip, right? The NIC, right? How about hitting the key on the keyboard, right? That also generates an interrupt, right? Okay. So So if we get the interrupt, then we're going to go to an interrupt handler that's going to move that frame into the computer and digest that Ethernet frame and do whatever we need to do with that Ethernet frame. Pass it up the protocol stack, right? Data link layer, network layer, and so on, right? So two approaches, we've discussed two approaches to I/O, polled and interrupt driven. You need to understand the difference, right? So Vinicius, what's the difference between polled and interrupt driven I/O? Lorena? The poll is always asking. With polled, we're continually asking the device if there is something to be read. Waiting for the device to interrupt us. Yeah. All right. Steph, difference? Excellent, excellent. And it could be for scheduling of programs, which is kind of what you described, or it could be for servicing some hardware like an an input device. We have an input output device here, right? And so did a frame come in or not? We could continually ask that NIC chip if there is a frame for us. That's a waste of CPU time because the CPU is asking that question. We could be executing an instruction, right? So we are either continually checking the status or we're not checking the status and we're letting the device interrupt the CPU so that then we would go and service the device. The trade-off is the code is simpler when we're polling. The code is simple. Do you have something? Yes or no? If you have something, I'll do it right now, right? Within one thread of execution, right? With interrupt driven, we have to go through this idea of pushing the stack and going to the interrupt handler and coming back, where were we, and all of that, right? So interrupt driven is more complicated but more efficient. Polled is simpler, but not as efficient. In modern computers for the operating system, it's interrupt, right? And so if you've been around for a while, you remember a day when Windows machines would very frequently turn blue, right? The screen, you'd have a blue screen of death, okay? And so there was a version, early versions of Windows did not support this type of behavior where the OS was always able to get control of the machine. They had something called cooperative multitasking. And with cooperative multitasking, it depended upon the programs calling into the operating system at some point. For example, if within each of the programs, there'd be a call that would cause the operating system to run. Right? It doesn't matter what call it was. In fact, there were multiple things that the program could be doing that would cause the operating system to run. What would happen in these early versions of Windows is there'd be a bug in the code so that you never got to the instruction that allowed the OS to run, right? And at that point, they had a timer circuit, but that timer circuit is what caused the blue screen to come up. Right? That timer circuit is what caused that blue screen to come up. And so this is one last topic while we're here. Programs have bugs. right? Unless it's the most simplest program, there are bugs in programs. Can we all appreciate that? We probably have created a couple in the past, right? So one thing that can happen is the machine can go to sleep or hang, right? And we're not able to use the machine anymore. This is a bad thing. Has any of us had this happen to us? The machine becomes non-responsive. Enos, it's never happened to you? Oh, it definitely has, right? It definitely has, right? Right. So there's a concept called a watchdog timer, right? And what it is there is a an interrupt here called NMI. This stands for non-maskable interrupt. And so the way this works is that this timer circuit gets set up with a period of time. Let's say 30 seconds. Right? If 30 seconds goes by without the program coming and resetting the timer, then it's going to cause the NMI to happen, and then the machine will reboot. Right? So it's a hardware mechanism that says if the program has gone to sleep enough that it doesn't remember that it needs to reset this timer, then after 30 seconds, the machine will recover from that software bug. This is called a watchdog timer. I guess if you go to the junkyard, there's a dog there that's making sure that you don't take anything or something, it's that idea. Or I have a couple of doggies at home that are very territorial, right? If anybody walks near the house, both the dogs let you know that there's a problem, right? And that's what this is all about, right? If this circuit connects to NMI, the non-maskable interrupt, then a problem has occurred and the whole machine starts. So this idea of masking means that we could cause some of the interrupts to be ignored, right? We have that ability to program what interrupts we'll respond to or not. The NMI, we cannot ignore it. We can't mask it out. Okay. That was interrupt-driven I/O. And polled is when the program is continually interrogating the chip to see if it has a frame or not. Poll. Okay, so Intel has a concept of a port. All right. So there's a couple of ways that we can view input and output. Right. We can view input and output as part of memory. So we could say that this NIC chip has an address in memory. So if we want to read the register that tells us whether there's a frame, we would read that address. Right. This is memory mapped I/O. Intel has a concept called ports, where it's similar, except we're saying those locations are special and we call them ports. And there are instructions that we use when we're dealing with ports, right? I think when we memory map things, it's simpler, right? But we can explore that. We can explore that further if you want. I think we're running out of time. Of polling? Well, architecturally, this can be happening outside of the machine. Okay, so for example, we could be pinging. You're a networking student, right? So when we could continually ping a device to see if it's there. All right. In fact, I did one project at one point. Just to give you an example, we could have a device here that we want to monitor, we want to ping. We want to ping that device, right? Now, the management station that's keeping track of things is over here. And we have the internet here. You with me? Right? So we're sending a ping here, right? What if we want to save what if we're paying for this internet service, most of us do, right? And we want to save on data, right? We could put a device locally here and here. And we'll have this device ping. And this doesn't cost us anything, right? Ping, 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 no charge, right? And here we could ping this device over and over again, no charge, because we're not using the internet yet, all right? At this point, when this device sees no response, it can then initiate a message to come back to tell this device, don't respond anymore, right? So this is polled, and this is polled, but this is an optimization that allows us to not use the network. Minimize the traffic. Exactly, right. Right. And this pattern, it exists in multiple protocols. But it relates to the idea of polling as part of the equation. All right, are we close enough for government work? All right, and we're going to have a quiz next time on the CPU chapter, right? Awesome. See you next time.